Glass is completely transparent, yet it begins as nothing but sand. A window pane can survive decades of rain, wind, and cold, yet it shatters from a single tap in the wrong place. A wine glass holds liquid without leaking a single drop, yet it has no seams, no joints, and no glue holding it together. That level of transformation, from gritty raw earth to something so precise, so clear, so controlled, shouldn't be possible. So how do factories turn ordinary sand into the transparent, smooth, near-perfect glass found in windows, bottles, and screens used by billions of people every single day? Let's step inside and find out. Most people assume glass starts in a mold, shaped, pressed, cut flat. It doesn't. The flat glass in every window, every mirror, and every glass door in the world is made using a process so elegant it almost seems accidental. The glass isn't pressed or trimmed into shape. It floats there, perfectly level, because of physics alone. It starts with a blend that looks nothing like glass. Silica sand, soda ash, limestone, and a small amount of recycled glass called cullet. Each ingredient has a job. The silica is the backbone, pure silicon dioxide, the same compound found in beach sand and quartz. The soda ash lowers the melting point, making the whole process more energy efficient. The limestone adds chemical durability so the final glass can resist moisture and weathering for decades. And the cullet, crushed recycled glass from previous production runs, helps the mixture melt faster and reduces waste to almost nothing. These raw materials are precisely weighed and blended in computer-controlled batching systems before being fed continuously into the furnace. That furnace burns at roughly 1,600 degrees Celsius, hot enough that the sand, limestone, and ash stop being solids entirely. They dissolve into one another and become a single continuous river of molten glass, glowing orange-white, flowing forward through the furnace like liquid stone. The furnace itself never stops. Glass plants run their furnaces continuously, 24 hours a day, 365 days a year, for up to 15 years before a furnace is shut down for rebuilding. Stopping and restarting a furnace is so energy-intensive and damaging that it's considered a last resort. From the furnace, the molten river flows directly onto a bath of liquid tin. This is the float process, invented in 1959, and it permanently changed the industry. Before it existed, flat glass had to be ground and polished smooth after forming. That was slow, expensive, and still imperfect. The float process eliminated all of it. Because molten glass is lighter than liquid tin, it floats on the surface automatically. And because both materials are in a liquid state, surface tension pulls the glass flat. It spreads to a uniform thickness without any rollers, any pressing, or any external force. The atmosphere inside the float bath is carefully controlled, a mixture of nitrogen and hydrogen, to prevent the tin from oxidizing and contaminating the glass. As the glass ribbon travels forward along the tin bath, it cools gradually from around 1,000 degrees at the inlet to roughly 600 degrees at the exit, a journey of about 60 meters. At that point, it's solid enough to be lifted off the tin on rollers, but still far too hot to handle without cracking. So it enters an annealing layer, a long temperature-controlled tunnel, where it spends several more hours cooling down in a precisely managed gradient. This controlled cooling releases the internal stresses built up during forming. Without it, the glass would be locked in a state of tension and would fracture unpredictably the moment it reached room temperature. Here's what makes the float process genuinely remarkable. The glass exits the tin bath with two completely different surfaces, and both of them are optically flat without any finishing at all. The bottom surface, which rested on the liquid tin, is mirror smooth because it was in contact with a perfectly flat liquid. The top surface is equally smooth from surface tension and the controlled atmosphere above it. No grinding, no polishing, no finishing passes of any kind. Both faces are ready to use straight off the line. That's why float glass ends up in everything from skyscrapers to telescope mirrors to the screen you're probably watching this on. At the end of the layer, Automated diamond-tip cutters score the ribbon, and controlled pressure snaps it cleanly into sheets. What entered the furnace as sand and powder exits as a perfectly clear, perfectly flat pane, ready to be cut to order, coated, laminated, or tempered for specific applications. But flat glass is only one form glass takes. Bottles and containers need an entirely different approach, one where the glass doesn't float. It falls. A glass bottle looks simple, round, hollow, seamless. But producing millions of identical bottles per day, each with the same wall thickness, the same neck diameter, the same weight to within a fraction of a gram, requires a sequence that completes itself in under 2 seconds per bottle. Container glass starts with the same core recipe: silica sand, soda ash, and limestone. Color comes from the batch additives: iron and sulfur for amber brown, chromium oxide for green, and decolorizing agents to cancel the natural greenish iron tint in clear glass. Up to 90% of a bottle's raw material can be recycled cullet from crushed old bottles, which lowers furnace temperatures, cuts energy use, and reduces the need for raw material mining. Molten glass exits the furnace in a continuous stream, and automated shears clip it into individual gobs, precisely sized blobs of molten glass, each one calibrated in weight to match the exact bottle being produced that shift. Each gob drops by gravity into a blank mold, where it's compressed into a rough preform called a parison, a thick-walled, sealed tube of hot glass with the neck already formed at the top. Air is introduced to create a hollow core inside the parison. Then the parison is transferred to the blow mold, the final shape of the bottle, and a timed burst of high-pressure air expands the glass outward until it presses firmly against every contour of the mold wall. The glass takes that shape instantly, and within seconds it's cool enough to hold it permanently. The entire sequence, from gob to finished bottle, takes between 1 and 2 seconds. A single production line runs dozens of molds simultaneously, each cycling independently. A well-run container glass plant can produce more than 500 bottles per minute from a single line, and most plants operate multiple lines without pause. Every bottle that comes off the line passes through automated inspection, sensors measuring wall thickness, height, diameter, and weight. Any bottle outside tolerance is immediately diverted, crushed, and fed back into the furnace as cullet before it ever reaches a shipping pallet. The waste rate on a modern bottle line is remarkably low, and what waste does occur never leaves the factory. The bottles pass through their own annealing layer to relieve forming stress, then emerge cool, smooth, and identical, ready for filling lines that may run just as fast as the glass line that made them. The flat glass in a window and the glass in a bottle share one weakness: if they break into large, sharp shards. For most applications, that's fine. But for car windscreens, shower doors, phone screens, and building facades, that's not acceptable. That's where tempered glass comes in. And it's one of the most counterintuitive things factories do to glass. To make it stronger, they first make it weaker on purpose. Tempered glass starts as standard float glass, cut to the required size and shape. It then enters a tempering furnace, where it's heated to around 620 degrees Celsius, just below the point where glass would start to soften and deform. At that temperature, the glass becomes slightly flexible throughout its entire thickness. Then it's quenched, blasted with jets of cold air on both surfaces simultaneously. The outer surfaces cool and solidify almost instantly. The interior is still hot and contracts as it catches up. This differential cooling locks the outer layers of the glass into a state of compression while the core remains in tension. The result is a glass under constant internal stress, and that stress is exactly what makes it strong. To break through the compressed outer layer requires roughly 4 to 5 times more force than ordinary glass of the same thickness. But when tempered glass does break, when that compression is finally overcome, the stored energy releases all at once. The entire pane shatters simultaneously into thousands of small, blunt fragments rather than sharp shards. That's not a flaw, it's the whole point. It's engineered to fail safely. Every car side window, every glass shower door, Every glass tabletop, all of them went through that furnace and that quench. The glass you can break with a hammer without cutting yourself is the same glass that withstood the force to begin with. That's how glass goes from raw sand to the flat, flawless panes in skyscraper windows, to 500 million identical bottles, to shatter-resistant surfaces engineered to fail without causing harm. Precision, chemistry, and physics working together in processes most of us walk past without a second glance. Until now.